In this clip, we will take a look at the problem-solving strategy named Divide and Conquer. Let's dive right in. This box represents the problem that we are trying to solve. Many larger problems can be considered as a kind of composite of multiple subproblems. In a moment, I will show you a couple of concrete examples of such problems, but let's first spend a moment describing the general idea of the problem-solving strategy. One of the key ingredients in Divide and Conquer is to discover how to divide the larger original problem into subproblems. Once divided, each of the smaller and easier to understand subproblems are solved, leaving us with sub-solutions. Finally, find a way to combine or deduce the sub-solutions into a solution to the original and larger problem, thereby conquering it. This strategy can be applied recursively. Let, once again, this large box represent our original large and complex problem. As we saw before, we might be able to divide that problem into smaller subproblems. If these are still too complex to solve, we can perhaps perform a division again, and again, and again, until the problems are sufficiently easy. Now we solve these small micro-problems, and we walk back up the recursion again, this time assembling solutions to the larger problems from the smaller subproblems. We do that one recursion step after the other, and end up with a solution to the final problem. So there are three things to consider. Can the original larger problem be divided into smaller subproblems? If so, how? How can we solve each of these small micro-problems? And once we have a solution to the subproblems, how do we assemble the larger solutions from the sub-solutions? Here are the same three steps printed on the screen again, as we are gonna need them in a moment. On the screen is now printed 6 letters in a messy order. We would like to sort them alphabetically, so let's see if we can divide the sorting of these 6 letters into multiple problems of sorting fewer letters. The sorting strategy that we will end up with is also known as quicksort. But let's proceed. For example, we could pick an arbitrary letter, say D, and generate 2 lists consisting of the letters that are smaller than and larger than D, respectively. In this example, B, A, and C would go in the smaller than container, while F and E would go to the larger than container. Now we have the letter D together with one list consisting of all the letters that are smaller than D, and another list of letters that are larger than D. If only the smaller than and the larger than lists were sorted, then we could just append them to either side of D, and then our original list would have been sorted. Notice that this is exactly the same problem as our original problem, just on smaller lists. Let's continue. In the smaller than list, we choose an arbitrary letter, say A, and produce a smaller than and larger than list, just like before. Here, nothing goes into the smaller than list, while B and C goes into the larger than list. Back up at the letter D, we now focus on the larger than list and select an arbitrary letter, say E. Again, we generate a smaller than and a larger than list, where nothing goes in the former, while F goes in the latter. Last, we proceed to the larger than list of A. Here we choose an arbitrary letter, say C, and generate a smaller than and a larger than list, with B in the former and nothing in the latter. Now, if only B was sorted, then we could just append it to the left of C, and then these 2 letters would be sorted. Wait a minute, B is already sorted. It's just a single letter. Let me get rid of this noise. Now we have a whole tree of individual letters, all of which are sorted by definition. Time for the assemble or conquer phase. B can be appended to the left of C, thereby obtaining the sorted list BC. BC can be appended to the right of A, thereby obtaining the sorted list ABC. F can be appended to the right of E, thereby obtaining the sorted list EF. ABC goes to the left of D, and EF goes to the right of D, and now the list is sorted. So the strategy was as follows. In order to divide a larger problem into subproblems, we chose an arbitrary element and generated lists of elements that was smaller than and larger than our chosen element. Each of the lists were now subproblems. The microproblems were trivial to solve, as they were just single elements, and a single element is already sorted by definition. Assembling the parent solution was done by simply appending the now sorted smaller than list and the now sorted larger than list to either side of our chosen element. If we assume that our original and unordered list contained n elements, then we can consider a worst case scenario and an average case scenario. In the former, we could be unlucky that our randomly chosen element was either the smallest element or the largest element on that recursion level. And in that case, we would have that single element in our hands, while all but that element goes to the same list, either the smaller than or the larger than list. So if we are really unlucky, we would only decrease our original list length with 1 for each level. And if there originally was n elements in our list, that unlucky situation would give us a whole n levels before we ended with only one single element in the last list. Each of these levels contains at most n elements each, so n recursion levels, which will handle at most n elements each, gives a total of big O of n times n, or n squared, elements to handle. In comparison, let's look at the average case. In average, the randomly chosen element would have around equally many elements in its smaller than or larger than sublist. Therefore, each of the two lists would be half the size of the original list. In average, we have previously seen how many times we can cut a set in half before landing on a set of size 1. That is, the logarithm of n, which means that we, in average, will have the logarithm of n levels, not n, because we expect the two sublists below each element to be more or less equal in size. At each level, we still need to consider at most n elements. So the total complexity in the average case is to handle big O of n times the logarithm of n elements. This is significantly better than big O of n squared. Let me quickly show you how this quickshort can look like in C#. Here's an example implementation of the quicksort algorithm. It operates on any type as long as that type implements iComparable, so that we can compare two elements of that type. So it takes as input a list of these types, and then the recursion begins. If the list has length 1 or 0, the list is just returned as is, because it's by definition sorted already. Otherwise, if the list has a length of 2 or more, we first find the position of our random element and then create two empty lists for our smaller than and larger than elements. Then all elements in the list is traversed. Of course, the randomly chosen element should not be included in either list, so we'll just skip that. Otherwise, if the current element is smaller than the randomly chosen element, it's put to the less list. Otherwise, it's added to the larger list. Now for the assembly phase. First, the less list is sorted by calling quicksort recursively on that. Then on the sorted result, the randomly chosen element is added. And then we call quicksort again on the larger list in order to sort that, and the result is appended to the right. Last, our merged solution is returned, which is now fully sorted. We have seen quicksort as an example of divide and conquer, where quicksort had a worst case complexity of big O of n squared, but an expected complexity of big O of n times the logarithm of n, other sorting algorithms have a guarantee of big O of n times the logarithm of n. One example is merge sort. The basic principle of merge sort is that if two lists are already sorted, like these two, then we can produce the combined sorted list by simply merging these two lists, and this can be done very efficiently by continuously consuming the smallest element from either list until both lists are empty. Merge sort, by the way, has another nice property. Because of the merging strategy, it can be used to sort arbitrarily large volumes of data using only limited amounts of main memory, for example to sort 5 terabytes of data using only 64 gigabytes of RAM. In a previous module we took a look at binary search. Here the original problem is the large list of data, and after finding the midpoint, the subproblem becomes the sublist of either the right or the left-hand side of the midpoint. Divide and conquer can also be used to multiply large numbers. Here the original problems are the large numbers, and the smaller subproblems occur by splitting the large numbers into smaller chunks and forming the larger result by the sum of appropriate products of these subnumbers. As a last example, divide and conquer can be used to deduce which 2 points in the plane that are closest to one another. If this is the original problem, the subproblems are formed by splitting the plane in two and finding the closest 2 points in the subplanes. There are other examples, but the main takeaway here is large and complex problems may be reduced to a combination of smaller problems, which again may be reduced to a combination of even smaller problems. The solution to the original problem is then formed by appropriately combining the subsolutions.